Okay, this is our extra special bonus lecture. If you just hadn't heard enough of my voice over the computer um, on special relativity, uh, which is really fascinating. So I thought maybe some people would want to listen in. So let's talk about special relativity. So most of what we've done until the last couple of weeks is what's called classic or Newtonian physics um, that happens on um, a human scale, right? When we get small in quantum, things get strange. But the same thing happens when we start moving really fast. And so when we start talking about fast moving objects, and we're talking about the speed of light here, this is called relativistic physics or Einsteinian physics, if we want to do that with Newton's law. So let's just figure out. I just want to give you some sense of what relativity means. So let's say you're driving in a car at 60 miles per hour, and you're on the moon. We don't want any friction here in the atmosphere. You throw an orange through your sunroof, um, and where does it land? Well, Newton's first law tells us um, that it will come back through the sunroof and land on your lap. In other words, when you throw um, the orange, it's moving at the same velocity that your car is. And if there's no force keeping it from continuing to move in that way, that's what the first law tells us, it will continue to move in that way, right? So you throw it up, um, there's no drag or friction on it to push it backwards, and so it's going to drop back down because of gravity and land right on your lap, which is one of those weird things about Newton. Uh, um, Obviously, on Earth, that wouldn't happen. If you threw your orange into the air and it was moving at 60 miles per hour through the air, there would be some drag force that would slow it down. And it wouldn't have the tires to push it forward in the way your car does. But on the moon, it's fallen right back down to you. Um, this is called an inertial reference frame. That means that everything in this frame is moving constantly at 60 miles per hour. And so we can treat it as if it were standing still in that inertial reference frame. There are no forces outside acting on it, causing things to accelerate. So let's imagine now that your friend Bill is outside and he's watching that orange get thrown in the air. Now, if he were going to draw a picture of it, it would look more like this down here, right? So it would look like um, the orange is going up in the air and coming down in the vertical direction. But he would also see it moving in the rightward direction with the car, and it would look almost like you had thrown it that way, in a projectile motion, and landing in the sunroof. So to Bill, it looks like that orange has traveled quite a bit farther than it did within your inertial reference frame. How does that make sense? Well, in classical physics, we just start adding our vectors. The true velocity of the orange is the sum of the frame's velocity vector, that is how fast the car is going, plus the orange's velocity within that frame, uh, it going up and down in your frame. And if you add those two things, you get this nice looking projectile motion. Okay, so in classical physics, we deal with that problem um, basically by thinking about how vectors work and adding the frame to what's happening inside the frame. Um, a little complicated, but we did that back in 151, and it's pretty manageable. So, what happened when Einstein started thinking about this when things go really fast? Well, Einstein was with other physicists struggling over some experiments that they were doing with the speed of light that suggested that the speed of light went the same speed no matter what reference frame you were in. And they basically just figured that the experiments must be wrong, right? Um, that the speed of light shouldn't be the same no matter what reference frame you're in. It should sort of change, like the speed of that orange changes depending on what reference frame you're thinking about. But Einstein started to think, well, maybe in any inertial reference frame, that is a frame that's not accelerating, the the laws of physics are the same, and that the speed of light is constant and is independent of the relative motion of the source. Um, okay, yeah, the laws of physics works, the speed of light is constant, we're okay with that. But then we start to think about that. What if, just to give you one example, what happens if you're speeding in a rocket near the speed of light and you shine a flashlight forward? That's weird, right? Isn't that light then going 2 times the speed of light? And isn't that impossible? That's where Einstein was starting to struggle, right? How do we deal with that? So let's look at our a little blue car example. And instead of using a blue car and an orange, we're going to use a rocket ship and a laser. So our ship is moving constantly at the half speed of light from left to right. I direct the laser up and down, and it hits a detector on the floor, right? Just like in my car, I would expect that light would go up and come back down into my lap. And sure enough, that's what would happen. Um, the velocity of the spaceship doesn't have any effect on that, because really, in some ways, we can think of ourselves as hurtling through space at really large speeds because of the expansion of the universe. But that doesn't affect what's happening in our inertial reference frames, right? So we would expect the laser to act just like it would on Earth. But now we have our friend Bill, who's floating in space in another rocket, watching you pass by, and he watches those photons go from your laser down to your detector, and they've traveled farther um, than they have in Bill's frame of reference, right? Just like the orange traveled farther. Um, but if we go back to Einstein's second postulate, he says the speed of light is constant and is independent of the relative motion of the source. Well, with our orange, it wasn't independent of the relative motion of the source. We added the vector of the car's motion in order to get the motion of the orange here. But here the speed of light is constant and it doesn't matter what the source is. So the speed of light should be the same for Bill as it is for you in your spaceship. Where's the trouble there? Well, for you, it's traveled maybe 5 meters, and for Bill, it's traveled 50 meters. If the speed of light is constant, that means the time the laser takes to hit the detector is longer for you, or rather longer for Bill than for you, right? Because it has to travel 50 meters at the same speed for Bill that it did 5 meters for you. And that's the hard part here, right? What does that mean? If the speed of light is constant, that means Bill's time is different than your time. And that's the kind of heart of relativism, uh, uh, is that time no longer becomes an easy thing that we can think of as being the same for all frames of reference, but instead it becomes relative to your speed. Um, this is called time dilation. And so we can talk about a perceived time, where if we call delta T naught the proper time, how long something happens, measured by an observer at rest relative to the event. And even that's a complicated and fraught idea. But let's not worry about that fraudness for the time being. So T naught is the proper time. We can find the time that it seems like, or the perceived time for an observer, by taking the velocity of the inertial reference frame of the event relative to the observer, right? How fast is the rocket ship moving past Bill? Divide that by the speed of light um, and put it into this equation. So what happens when v is really small, which is to say anything that happens to us on Earth? This term is 0, 1 minus 0, or a very small fraction, very close to 1. That square root term makes it even closer to 1, and t naught is equal to t. Okay, but if v squared starts to become a significant fraction of c, um, then delta t starts to be different from delta t naught. Okay, so t naught is that laser hitting um, the detector for you, how long it takes for you. This is how long it takes for Bill. Okay, so if you're moving half as fast, right, then this becomes half. 1 minus a half becomes a half. Square root of a half is like 0.7. Okay, so let's say it takes, this is ridiculous, but a millisecond for you. This is going to be a millisecond divided by um, 0.7. So it's going to be about, what, 1.3 or 1.4 milliseconds for Bill. Okay, so that's what we mean by time dilation. When something happens in a frame that's moving some significant fraction of the speed of light, the observed time in two different reference frames becomes different. We can say a similar thing about length, right? So if the speed of light is the same and the time experienced by the observers is different, then the length is going to be different too, how far that light has traveled or whatever it is you're watching. The symmetry of these two equations suggests what's called the space-time continuum. And this is something that's happened over and over in physics, right? At some point, people thought electricity and magnetism were separate things, and then they kind of figured out that they're deeply interrelated with each other. Um, Matter, we thought that mass, particles, and waves were completely different, but it turns out that they're intimately related to each other. Matter and energy equals E equals mc squared is a way that we thought that matter and energy were not deeply linked, but it turns out that they're the same thing. And so here, space-time is happening. That converging of two really different ideas, it turns out that they can be converted into one in another. What does that mean? It's a really odd concept. Well, let's think a little bit about that space-time interval as a dimension. So while time and length are different observed by you and Bill, the space-time interval between that photon leaving the laser and hitting the detector is the same. So what does that mean? Well, let's think about time as a fourth dimension here, in addition to the 3 dimensions of space. So here in the image up on the right, it looks like these two vectors are different lengths, right? And you'd think I was crazy if I told you that they were the same. Um, this is like looking at space on its own, right? So we look at space on its own and we say that the time is different for Bill and you, or the length is different for Bill and you. But this is a 1D image, right? And imagine that the real vectors are these two vectors, and I just turned them on the side and I rotated them. So this red one looks like it's only going that far. But in 2D, there actually are the same length, right? That the length here is the same as the length here. So when we look at this in 2D, we can see that in fact they are the same. If we try to look at it in 1D, we get really confused because it looks like they're quite different. This is space-time here. This is looking at Bill and you's perspective in terms of a 4-dimensional space. This is us getting confused because it doesn't seem to make any sense that their time is different. And so space-time adds a dimension that if we think in that 4th dimension, which is a lot easier said than done, uh, then these vectors are going to be the same length. In other words, in space-time, the interval between that photon leaving the laser and hitting the detector is the same. In just space, it's different. In just time, it's different. But in space-time, with all of the dimensions accounted for, it is the same. So you all understand relativity now, right? All right. That's just an attempt to start thinking about what that might mean. All right.